This is our project advancing environmental mapping and forest health assessments with drone imaging. So the background behind the project is that the USDA Forest Service, currently the way that they monitor forests around the entire country is by using ground-based manual field surveys. And the problem with these type of surveys is that they tend to be very time consuming compared to like an aerial survey or an automated option. They're more expensive because there's more people in the loop compared to our solution, and they're restricted in their spatial coverage that you can only survey where a person can go. And the problem with a lot of existing research with automating this process of manual field surveys of forest monitoring is that it tends to focus on more isolated components instead of a complete like blended system. And our research would bridge the gaps. So our solution in this case would be to create a UAV capable of capturing high resolution photography. And then we would fly the UAV over designated areas that require forest health assessments. And the UAV would then collect photography, which would then be processed on the ground. So that way we could save the storage space on the drone for imagery instead of using like valuable storage for image processing. And then we'd send the data to agencies that would benefit from it, such as the Bureau of Land Management, United States Department of Agriculture. And materials that we've used a Volantex Ranger 2400. The reason why we chose that was due to its larger wing aspect ratio, which allowed for high endurance flights, longer range, larger payload. Although that does come with some downsides, it's a lot more difficult to fly a UAV with a larger wing aspect ratio because it's a little bit less stable and maneuverable. And we also used a FlySky FSI-6X as the transceiver system. And a 5,000 milliamp hour LiPo battery was used to provide power to the drone in flight. And the great thing about the LiPo battery actually is that it also acts as a counterweight. So we didn't need to install any lead counterweights on the wing in order to create a good center of gravity to fly. We also used a Raspberry Pi as a camera trigger, and for flight instruments with the Raspberry Pi in order to allow autopilot in the future, we gave it a BN880 GPS module and Berry IMU V310D-OF. The Berry IMU is the one that has like a lot of flight instruments like an altimeter, gyroscope, things like that. And then the GPS module is more for make sure it's following the course that we would use for autopilot and for recovery of the drone. And we also use a Raspberry Pi RGB HQ camera, high quality. So a lot of imagery uses NVDI, and the path our research has taken was at some points we were thinking about using an IR camera in order to get NVDI imagery, but we've also thought about using an RGB camera and then creating a neural network to estimate NVDI values using the RGB. Um, so capturing aerial photography. There's a lot of nearby parks near ASDRP. There's the Forest City Sun Park State Park, Calera County Park, Castle Rock State Park, and a lot of other nearby state parks. I think we went to an open space preserve last time. I forget exactly what it's called, but not too far last time we flew it. It was like 5 minutes from the lab. The drone would fly under 400 feet, and if in the future we do implement autopilot, we would apply for FAA Part 107 waiver, which would allow us to use autopilot to fly outside of line of sight. And here's an instance of NDVI imagery. So as you can see, the negative values in the imagery corresponds to less vegetation, whereas the more positive values tends to correspond to more vegetation. It's not perfect, as you can see. It fails to capture, or it ends up capturing vegetation that doesn't exist through the reflection. And that's just because NDVI relies on IR values to approximate vegetation. So results. We do hope to see that our methodology is cost effective, quicker, safe, and creates more replicable results in other research and current methods of forest surveys. In the future, we're hoping that we could automate the drone path through GPS or send real-time data to our computer. And if we succeed, we could use our work in large-scale forest assessment and later move on to using a larger non-commercial airframe, which would allow for high endurance. It'd be a lot more optimized for our goals and so forth. We could also use this for crop assessment and search and rescue. In terms of current progress, we've currently already had our drone purchased and we assembled everything. We got the transceiver system together and we integrated a Raspberry Pi camera with the plane. We've done test flights over two different parks. And during the most recent one, we did manage to capture some imagery, but we had a rough landing. So the SD card popped out and it broke in half, which is pretty unfortunate. Um, we're hoping to collect data soon and we're having some trouble with stability because of trying to fit the Raspberry Pi into the UAV and at the same time put the battery into the right position has been really hard. Even though the drone can easily carry the weight of both of them, the problem more so is being able to put everything in the right spot because we need to put the battery closer to the wings in order to make sure the center of gravity is in the right spot. And we've also built a neural network to classify NDVI images based off of RGB data. So acknowledgements, oh, it shouldn't be Dr. Robert Downing, it should be Mr. Downing. But Dr. McMahan for guiding us and showing us how research is done, and Mr. Downing for procuring materials and providing insightful advice.